Good afternoon. Thank you guys all for being here, and thank you to the committee for the opportunity to share our research with you guys today. I am Carrie German, a group leader at CFD Research Corporation, or CFDRC, in the Computational Medicine and Biology Division. And as you may have gleaned from Dr. Ingver's talk earlier this week, we focus on developing computational models of physiological systems through various collaborations. So this talk will kind of just give an overview of some of our different capabilities, ways that we've implemented these models. And while it will just scratch the surface of what we're able to do, I'm hoping to kind of show how these models can, sorry, I'm hoping to show how these models can be used to optimize chip design, both prefabrication and post-fabrication modification, as well as to support the demonstration of physiological relevance of these systems. So as we all know, the drug development process consists of a series of in vitro, animal, and human studies where the overall goal is to develop a safe and effective medication. Various efforts are made along the way to translate these in vitro and animal preclinical results to the human condition. And though there's been debate, of course, over where microphysiological systems will fit into this drug development process in the future, I think the general consensus is that they will play a key role in the translation from in vitro to the in vivo condition. So an additional piece that plays a key role is the computational modeling part. So as Dr. Schuler indicated earlier, PBPK modeling has been around for decades, and it's used to basically indicate how the drug distributes to the body and predict how the drug can distribute to the body. So through various collaborations with government, industry, and academia, we have developed numerous PBPK models linked to PD for numerous animals, many of which you see here, as well as humans. And we use a first principles modeling approach where physics dictates the transport in our systems or in our humans, our subjects, and also the physicochemical properties of the drug as well as the properties of the tissues dictate how the drug distributes into the different organs. So we actually can use this same approach for in vitro systems modeling, taking only into consideration now the material makeup of the system. And this type of approach actually helps us to enhance our ability to translate from the in vitro to the in vivo much more smoothly. So when we start this, we got to develop computational frameworks for the microphysiological systems. And the way that we do this is we start by replicating the geometry. And there's typically two different approaches that we can use. Compartmental modeling, which is very, very commonly used in PBPK modeling because it's very nice for representing well-stirred compartments. They're very fast running and they're relatively easy to build. However, these models do have their fallbacks where they can't resolve the spatial gradients and modeling multiple species becomes really cumbersome. And the 3D approach can actually compensate for some of these things where we can actually have spatial resolution of gradients in the system, and it's actually due to the modular nature, we're able to model multiple species much more smoothly. It also has a nice visualization component. However, anybody who does computational modeling knows these are very expensive and can take days, even weeks to get a final solution. So we at CFD Research have kind of come up with an alternative that brings together kind of the best of these two worlds using a reduced order modeling approach, which we term quasi 3D or Q3D, to model these different channels in the microphysiological systems, as you can see here. So we still retain the spatial resolution. We resolve the gradients in the direction of flow, but we also still allow species transport and cross flow as well. So these still retain the advantages of the 3D that we can model multiple systems, and we have those visualization components as well. And then of course, we also have the opportunity to combine them all and see which one is the most efficient and best model, depending on the system that we're modeling. So just because it's a new kind of a different approach, we wanted to make sure that we rigorously tested this Q3D approach and make sure that it could replicate both the simple ODE system or compartmental system as well as 3D. And here you can just see we've done some simple test cases where the PK profiles in a 2-channel microphysiological system overlap exactly for both the Q3D versus ODE case, and as well as 2 different meshes and multiple other meshes, but for the 3D and Q3D case. So I'll kind of start into more of some of the examples of the things that we've been able to do. So I'm starting with a conventional in vitro system. I know it's not a microphysiological system, but it's kind of a nice place to start. We don't have flow. It's diffusion driven, and it's actually a relatively simple geometry. So we can actually use compartmental modeling approaches to model these different pieces where the different medias are represented as different compartments. Cell membranes, intracellular organelles can even be represented in these types of models. So transport within the system goes across these boundaries. We integrate over the boundaries to represent diffusive flux across the membranes, the cell membranes. And the drug metabolism is actually represented in the cellular compartment. So we typically use Michaelis-Menten kinetics here to represent drug metabolism, but this is also used for us to model nutrient metabolism, which is also important as well. So in the bottom, you can see just a well plate simulation where oxygen distribution is represented with respect to the media height. And so you could see how we could do that, plot these for different times and actually optimize our media change protocol, as well as our volume conditions to enhance our quantification efforts. So probably moving on into the more exciting organ-on-chip pieces. Once we add the perfusion piece, it doesn't really completely, we don't have to go recreate the wheel here. We're still looking at the same kind of process. We still recreate the geometry depending on what we've got. On the left, we have a standard linear channel. Those obviously can be resolved with Q3D geometries. On the right, you can see a collaboration with Synvivo where we have a more rounded geometry. So Q3D is not as effective here. We have to use more 3D geometry resolutions. So after we recreate the geometry, we have to assign volume conditions and boundary conditions. This is just like your typical conditions, viscosity, diffusion coefficients, things like that. And then boundary conditions, we can set our flow rates as well as our inlet and outlet pressures, and then let the system solve itself through different well-established flow characterization equations. So once we've got this all working together and we can run a test model, we can then look at optimizing these conditions, these flow conditions to show the physiological relevance of the system. If you look at the plot on the bottom, next to the flow-dependent shear stress is SS. You can see how we can modify the flow in the system to change the shear and make sure that we are replicating what we should be seeing in vivo. On the side with this in vivo, we can see how this type of modeling can be used to optimize your design of your chip. And in this case, we can change the pore density to make sure that we're achieving the concentration needed in that target tissue chamber there in the center. So after we do these optimization studies, we can then move into predictive studies, which you can see at the bottom for single channel perfusion versus dual channel perfusion. On the left of these two pieces, I hope it's left. Yeah. So if on the left, you see the simulations for these two types of perfusion, and then you see the experimental results that are in very good agreement with these on the right. So it's not just modeling the chip, right? There's a lot of pieces, and there's been a lot of discussions on this throughout the sessions that I've attended. It's also modeling these peripheral components. There's been a lot of talk about tubing and the absorption of these drugs or compounds that we're looking at into the tubing. There's a lot of other phenomena that can occur within the reservoirs, the valves, the sensors, the pumps, whatever other pieces that we want to include. So we've worked on integrating those pieces, and actually here we can kind of show some of our multi-scale modeling capabilities to enhance our model efficiency. So through previous collaboration with, Charité, they developed a liver on chip model, and we were trying to simulate APAP distribution throughout the chip. So the model itself had to be resolved in 3D, but the underlying system of tubing and piping was actually modeled in Q3D. So we could integrate these two systems and allow them to work together more efficiently to get the results that we needed. On the right, we can see the continuity of the two models so that the APAP that was administered to the bubble trap actually does flow throughout the whole system. So another subject that we've seen and heard a lot about this week is PDMS partitioning. So a lot of these different systems include PDMS, and the loss to that PDMS has to be considered for any of these different kinds of experiments that we're conducting. So in collaboration with Weiss, we worked on implementing a model, a Q3D CFD model for drug absorption into the PDMS, where this is where we can see the spatial gradient without the actual 3D representation on the right, where there's a 10-hour inflow of FITC and then a 5-hour washout, but we still see the absorption and spatial gradient despite that presence of a 3D meshing in the top channel. We also compared the results in our Q3D model for the concentration of FITC with respect to the distance into the PDMS with the experimental results. And we have very nice agreement for our first implementation of this model. So we're excited to see where else we can actually apply this type of modeling. So as I said previously, modeling multiple species can be an important part of what we're looking at in these chips, particularly if you have interacting species or if you have metabolism where some kind of metabolite is produced. So that's obviously, we need to be able to model both of those simultaneously. So this is just another example using the Weiss chip where we've modeled the distribution of glucose into the system, as well as ammonia production and albumin production in the system. And so these were all modeled simultaneously, which is a huge advantage, not having to recreate the model every time. So the next step after we've got our chips, we've got our outside pieces, we've done all the PK modeling. We also like to link these to some additional types of modeling like PD modeling as well as tox modeling. So we've done various efforts in looking at this. This is kind of an older collaboration with Weiss, looking at the heart chip, where we can see dose-dependent changes in the membrane potential. Well, on the chip, we do model the drug PK with the different losses and binding and flow, but then we can also use that to simulate drug toxicity using the drug concentration for ion channel binding. And then you can see in the bottom corner, I know it's already stopped, but it's the replication of the electrophysiology of the health, not the tox affected one, but just under the normal conditions where we mimic what is seen on chip and then what's seen for the virtual patient. So we've modeled these individual chips and we've looked at all the things that we can do externally, but now we want to look at, can we model multiple organs on a chip? So you've probably heard Casey and Diogo talk earlier about their multi-organ chip, their 4-organ chip containing skin, bone, heart, and liver. So we help to support those modeling efforts. And we just exactly like we would do a single chip, we've just done it for all 4 of these different tissue chambers. We have characterized species transport, and then we characterize metabolism of the drug doxorubicin into doxorubicinol. And we did this for both a functionalized membrane and a non-functionalized membrane to see how that membrane functionalization affects the PK results. And so I won't show both because they did. So I will show how well we were able to match the experimental results for both the parent drug doxorubicin and the metabolite doxorubicinol in all 4 chambers of the chip. And then finally, I want to wrap up with kind of how this kind of can all tie together and how we see in silico modeling supporting IV-IVT. So in collaboration with the FDA and some ongoing work, we have developed this with the Office of Generic Drugs as kind of a preliminary approach. So we go through and we characterize the compound. We find as much data as we can in literature. We're trying to do this all based on literature and not having to conduct new experiments. So in our case, we also have IVRT experiments, not just in vitro, metabolism and transporters, but also IVRT. We have ex vivo IPT experiments that we can also simulate. And then we try to use those same exact parameters that we use in each of these models and keep them the same, keep them constant. So permeabilities, partition coefficients, dissolution rates, all of that is kept the same across all of our models. So this is just an example that we've done with loteprednol etabinate. It's applied to the eye, an ophthalmic ointment. We collected a lot of data from literature, but of course they wasn't all there. And this is where I see MPS playing a really key role, is determining the values of some of these parameters where they can reduce the amount of calibration that's required. After simulating IVRT and matching the experimental results for that, again, using first principles approaches, we moved into corneal penetration studies. So we again found this data in literature, and using the thicknesses of the tissues and the Franz cell setup, similar to what we would do with the well plate setups, we were able to characterize species transport through the cornea. And again, using those values, we use those same values for topical application of the ointment and are in generally good agreement with that data as well. So in terms of current and future directions, some of these things are ongoing. Obviously, you've seen some of our on-chip pharmacodynamics modeling, but we want to extend that and look at some more ways to expand that portfolio. We've heard a lot about on-chip genomics and how that can affect metabolism and different other PD effects. So we would like to integrate those as well. Obviously, more toxicity, and of course, the whole reason that we're here looking at how we can have MPS inform IVIVT. We'd also like to look at moving into modeling disease states and incorporating bioanalytics into our modeling pieces. And we're always looking for collaborators and ways we can expand this portfolio. So I think to finish it off, I will just say thank you to our many collaborators, without which this isn't possible. Our models don't work the way they should. So thank you to all of them, and I'll take any questions at this time.
Thank you. We have time for one or two quick questions.
Hi, great talk. I was wondering if your models are able to account for like remodeling of extracellular matrices, and especially a lot of interest in like vascularization or tissue breakdown, because a lot of what you showed seemed more like static blocks. You kind of like pre-render the entire system, and then you do computational fluid dynamics to see like the dead zones.
Yes.
But like, let's say you have a hydrogel that over time gets remodeled or breaks down. Can your models, or are you looking for ways to also put that into your processes?
Yes. So we can do deformation, and so we have looked at that, but we haven't actually done like the erosion of the matrix or laying down of a new matrix. So I think that would definitely be an exciting avenue to pursue.
Thank you.
Thank you.
I'm Rachid from Geraldine Biotech. I have a question about the microscale modeling versus macroscale modeling for microphysiological system. First principle, with the microscale modeling, there are a lot of assumptions for the rate constants that cannot be really measured in MPS systems. And how do you handle the sensitivity of the parameterization and extracting the information from the chip experiments? Is this the ODE path versus the CFD, more PDE path is more reliable based on your experience?
So that's a really good question. I would say the ODE path is definitely, I don't know if it's even more reliable. It's probably the easier path at the moment, but I think we are going to have to move into the CFD path. It's just I don't know what the path is to getting there yet.
Thank you.
I had one quick question.
Yeah.
I've admired the CFDRC work for many, many years. Does your quasi 3D simulate the blurring of a concentration change due to Poisson flow?
So that's a really good question too. I actually would have to talk to our coding guy on the back end of that. I'm not sure.
The reason I ask is there's a very interesting photograph of Steve Quake's circular mixer / pump that shows a parabolic wavefront that is stuffed inside of itself. And I've always wondered the extent to which you can fake that without having to do full 3D.
Yeah, that's an interesting. I will get back to you.
Thank you.
Yes.